the following slides will briefly explain the fsolve tool available in Matlab, through a practical example, in the field of chemical reaction engineering. In particular, the tutorial will briefly explain the concept of the numerical solution of a single equation, or a system of equations. Then, the description of the Matlab files, required to use fsolve, will be followed by the explanation of the main options of the tool. Finally, a practical application of fsolve, will be shown by means of a thermodynamic equilibrium calculation. So, let's start with the concept behind fsolve. The target of fsolve is to find the value of the independent variable y, such that the function f is equal to 0. This can be mathematically translated in the solution of this equation. In case of simple mathematical functions, for example the linear ones, the solution can be found analytically. Nevertheless, in the case of chemical engineering problems, chemical reactions are involved. Thus, the solution of highly nonlinear functions must be found, and an analytical solution is usually not available. Consequently, fsolve searches the solution, numerically. Since we are dealing with nonlinear problems, multiple solutions exist. Therefore, we must provide a first guess value, to let the solver find the only solution of interest. The closest is the first guess, to the correct solution, the less are the iterations needed to find the correct solution. If the first guess is too far from the correct solution, it can happen that it's too close to another solution, which is not characterized by physical meaning. In this case, the fsolve will find the wrong solution, and we will have to restart the procedure, with a different first guess value. Therefore, it is crucial to choose good first guess values. Since fsolve is a Matlab tool, it needs a Matlab program, which must provide both the first guess and the equation to fsolve. In case of a system of equations, the vector of first guess values and the system of equations will be provided instead. Moreover, the Matlab program should receive and store the output of fsolve, which corresponds to the solution of the problem. By doing so, the user can easily perform post-processing operations, such as conversion, selectivity and yield calculations, or post-processing plots, to effectively show the results. We move now to the description of the Matlab program, and the explanation of the setting options of the fsolve tool. The Matlab program should be divided into two files. The first file is the main.m. This script leads the solution of the problem. Indeed, it computes all the constant parameters required by the function f, and call the fsolve tool, as we will see in the next slides. Finally, main.m execute all the post-processing operations. The function f is contained into the second script, that is equilibrium.m. It is important to remember that this script is a function script. Thus, it must have the same name of the function contained inside. In this script, we must write the functional form of the equation, or system of equations, to be solved. Moreover, it must contain all the parameters, dependent from the variable vector y. Indeed, fsolve changed the value of y, at each iteration of the numerical procedure. Thus, fsolve must be able also, to recompute the non-constant parameters, at each iteration, by means of the function script equilibrium.m. The program, just described, translates into the following algorithm. The user starts to run the main file, which calls fsolve, after computing the constant parameters. Then, fsolve starts the numerical procedure. At each iteration, fsolve evaluates multiple times the function f, until it finds the best y for the next iteration. Once the best y is found, fsolve checks if the system of equation is solved by means of the tolerance specified by the user. If so, the solution is stored by main.m, otherwise, fsolve starts a new iteration, until convergence is reached. The fsolve options must be set before calling the tool. Optimset is the routine, which must be used to accomplish this task. The disp option is the display preference. If we set to iter, fsolve will display the results of each iteration. In particular, The fx and norm of step can be checked. In a correct run, the first one should monotonously decrease, whereas, if fsolve is not converging, the first one becomes constant and the second one becomes smaller and smaller, until the fail of fsolve. If we observe that fsolve is converging, but stops because it reaches max iter or max fundavels, we can just set higher values of these two parameters, and try again. However, a max iter above 1200, and max fundavels above 12,000, are usually not necessary, if the fsolve is properly used. Moreover, it is important to notice that, in this tutorial, we will use the default tolerance, but, the user can specify lower values by means of the keywords reported, and optim set. Once understood the working mechanism of fsolve, we can apply it to a case study. In particular, we will solve an isothermal reactor at equilibrium conditions, to better understand the fsolve application, in the context of chemical engineering. In our case, the inlet stream of the reactor is fully characterized, and the reported chemical reactions are sufficient to describe the thermodynamic equilibrium. The target of the problem is to calculate the composition and temperature of the outlet stream, considering that the thermodynamic equilibrium conditions are reached inside the reactor, and that an 85% conversion of methane must be ensured. By applying the material balances, and the stoichiometry of the two reactions, we can describe the molar fractions in the outlet stream, as a function of the two extents of reaction. The first extent can be computed from the required conversion of methane. Thus, we obtain a system of two equations, characterized by two unknowns, by means of the thermodynamic equilibrium, imposed on both the two reactions. The two unknowns are, the temperature, and the extent of the water-gas shift, side reaction. This represents a typical problem which can be solved with the fsolve tool. Nevertheless, before start writing the code, we must choose the proper first guess values for the two unknowns. As previously explained, we should choose two values with physical meaning. Consequently, we can select the inlet temperature, and an extent of the side reaction equal to 0, since it is not useful for the product. Then, we must check that the first guess does not generate negative molar fractions, and, finally, we can start writing the code. The first thing that we have to write is the order of the species, which will be consistent in the whole program. By doing so, we can always check this order if we don't remember it, thus avoiding mistakes. Then, we can start to write the section for the computation of constant parameters. In this section, the stoichiometric matrix is included too, and it is built with 1 column per species, and 1 row per reaction. This order can be reverted, only and only if the equilibrium.m file, presented in the next slides, is consistently modified. Then, we declare our first guess choice. Finally, it is important to mark all the constant parameters that we wrote as global. In this way, they will be accessible also from the equilibrium.m. We call fsolve, as previously discussed, and, then, we store the results of the extent of the second reaction, and temperature, in lambda, and t. Finally, we use fprintf to print the results on the screen as we will see later. It's important to notice that, when we want to put in the text, the value of a variable, by means of fprintf, we must specify the type of the variable, preceded by %. In this case, f means floating point number, and \n means go to a new line. Moreover, we must specify, after the text, the name of the variable to put, adopting the order of appearance of the variables in the text. Finally, we must write the equilibrium.m file. As previously mentioned, this is a function script file. Thus, the first line must be composed of the keyword function, the name of the output, the name of the function, which must be equal to the name of the file, and the input y. At the first iteration, the value of the input is our first guess choice, whereas, at the following iterations, the value of the input is decided by the fsolve tool, as previously discussed. In the second line, we must repeat the global variables, to ensure their visibility in the function. Then, we can rename the independent variables, to ensure a better readability of the code. Then, we write the section required for the computation of y-dependent parameters, that are the equilibrium constants, and the activity coefficients of the species, and, finally, we write the two equations. It is crucial noticing that, the target of fsolve, is to find y values such that fy values are 0. Therefore, the equations in the system must be written in this form. If we wrote properly the code, we can just start the run of the main file, and we should obtain, in the Matlab screen, the values shown in the green box, which represents the correct solution of the reactor. Thank you for the attention and, see you at the next